Well, good evening, everyone, and welcome again to our WIMBA to talk about Chapter 15 in Module D. Chapter 15 is, and actually Module T both, are associated with scheduling. And if we look at the course framework, we started with forecasting, and that fed into aggregate planning, followed by the master schedule, which again is a schedule by end item. And then we made some determinations about how much to order and when to reorder, and how much safety stock to carry, which impacted our service levels. And then last week we talked about how to handle component inventory with materials requirements planning. And so now, after we've done the materials requirements planning, now we're ready to schedule making or assembling the various components. And so that's basically what Chapter 15 is about. So Chapter 15 has 4 chunks of models, and we're going to talk about each one of these. And the book provides us with some heuristics or some rules that work very well in terms of doing scheduling. And then just as an FYI, scheduling is very difficult to optimize because the number of combinations is exponentially large as you increase either the number of options available. So, for instance, if you wanted to look at how many different ways you can schedule, 6 jobs on, 4 stations, then that would be, the combination of, 4 jobs on 6 stations. And again, we talked, well, I don't know, we didn't talk about that, but we talk about that in statistics. And that's just going to be 4 factorial over 6 factorial times 6 minus 4 factorial. It's a big number. Okay, I guess the bottom line is it's a big number. And so what we're going to talk about in Chapter 15, we're going to talk about the assignment heuristic. We're going to talk about some heuristics for scheduling a single station and as well as 2 stations. And then finally, we're going to look at staff scheduling. So any questions before we jump into Chapter 15? Okay. So the first technique in terms of what Chapter 15 talks about is the assignment method. And really what this is it's more of a matching. How can we match what we need to do with the resources we have available such that we either minimize or maximize some parameter? Typically, these are minimization problems. So the book does have the heuristic in it, but what I wanted to do this evening is just go over the heuristic with you and go through an example. So as an example, let's say we have 4 offices and we've hired 3 people, and we want to know what is the best assignment of these people such that we can minimize the relocation expenses. And those relocation expenses are shown in the grid. So, for instance, if we assign Jones to Omaha, it's going to cost us $800, etc. All right? Now, the first thing to notice in these problems is the assignment method requires an equal number of rows to columns. So you'll notice we have 4 columns and only 3 rows. So what we have to do is we have to add something called the dummy variable, and I'm going to try to add it here. And so this dummy is going to have 0 costs associated with it, all right? So what I'm going to do here is just put that in, all right? And you can see now I have a balanced 4x4 matrix, and I have this dummy candidate that, again, it's just going to be 3 people are going to go to 3 offices, and the 4th office is not going to get a new hire is basically what this means. All right, so this heuristic starts off after you make sure you have the same number of rows and columns, is you're going to subtract the smallest number from each row. So if I go to the first row it looks like the smallest number in that row is $800, and you can see it. And so what we're going to do is we're going to subtract $800 from all the values in that row. And so if we do that, what will happen, let me get my cursor over here. So 800 minus 800 is 0, and then it's going to be 300, and then it's going to be 400, and then it's going to be 200. All right. So what we did with the Jones row is we subtracted 800 from each value in that row, and we got the resulting values shown there. Okay. And then what we do is we go to the Smith row. And the Smith row, if we look at the smallest value in the Smith row, it is 500. So again, we're going to subtract 500 from each value, and we'll get the following. Okay, and so we get those numbers there, okay? And then finally, we do the same thing for the Wilson row. And again, the smallest number in the Wilson row is 500. So again, we're going to subtract 500 from each of the values in the Wilson row. And we're going to get the following. And sorry, my rows and columns don't add up, or line up. Okay. So that's really the first step, is we identify the smallest number in each row and we subtract it from all the values in that row. So any questions on step number 1? Okay, step number 2 is we're going to do basically the same thing for the columns. All right, so let me just put my dummy variable in here. And so if I look at the first column, the first column is basically zeros. So the first column is going to stay as is. It's going to be basically subtracting 0 from everything. The second column, the Miami column, is basically going to stay the same as well, because you're going to take 0 away from everything, and that is, again, the minimum of that particular column. So let me just put these in here. So the second column stays the same because we're taking 0 away from each number, which keeps it the same. And then if we look again at the fourth column, the Dallas column, again, that's going to stay the same because the minimum number there is 0. So that stays the same. All right, so we're going to keep basically just keep those numbers the same there. And the same deal with the New York column. The smallest number in that column is 0. So again, we're going to just subtract 0 from each of those. And essentially that column stays the same. Okay, so the first 2 steps are just subtracting the smallest number from each row and each column. Okay, so any questions on that? Okay, so the fourth, well, here, let me go to the next slide. So I'm going to just hold on here. I'm going to try to make these smaller. Hold on, if I can. I guess I can't. Okay, so here I'm going to try to put these, just redo these over here. Sorry about this. This will take me forever. And let's see, this one, 0. And then the last one is all zeros. It's a dummy. Okay, so the next step is you want to draw the minimum number of lines through all the zeros. All right, and the key word there is minimum. So if I look at what is the fewest number of lines I can use to draw, to cover all zeros, it would be 2 lines. All right, and these have to be either vertical or horizontal lines. You can't do diagonal ones, okay? So if I look at the minimum number of lines to cover all zeros, it'll be 2. Now, you can see that I have 4 rows and 4 columns. So the rule here is if the minimum number of lines is equal to either the number of rows or columns, you can stop and you can make the assignment. If it's not, if it's less than that, then you go to step 4. All right, so you can see we can't make the assignment yet because the minimum number of lines does not equal 4. So step 4 says you subtract the smallest number from all the uncovered numbers. All right, so if you look at all the uncovered numbers, here they are. Okay, and so it looks like the smallest uncovered number is 200. So what we're going to do is we're going to subtract we're going to subtract 200 from all of those uncovered numbers. All right, and so if I do that then, and by the way, you leave the lined values the same except if they're at the intersection. If they're at the intersection, and then in that case, you're going to add what you subtract. So the first row is going to be equal to this. And then the second row is going to be equal. Again, we're going to take 200 away from each value. So that's going to be 600 there. And then that's going to be 100 there. And then the third column, again, we're going to take 200 away from all the values there. And then 800, okay. Now, the intersection there where the dummy and Omaha meet, that's an intersection. Do you see the lines here where they intersect? So basically what we're going to do is we're going to add whatever we subtracted there. So we're going to put a 200 there, and then everything else comes down the same, okay? And so once we do step 4, then we go back to step 3. We're going to draw the minimum number of lines to cover all zeros. And if those equal 4, then we can stop. We can make the assignment. If not, we have to go back to step 4. All right? So if I do that, again, I have a line there, and I have a line there. And then let's say I have a line there. Okay, so now I have 3 lines. And again, it's still less than 4 what I need, so I have to go back to step 4, and I'm going to subtract 100 this time because 100 is the minimum number of what is uncovered. All right, so what I'm going to do here is I'm just going to type these in real quick. So I'm going to have a 0 there, a 0 there, I'll have 100 there, and a 0 there. And then I'm going to then this next one is going to be what, 700 or 800, and then 500, and this is going to stay the same at 100. And then coming down here, this is going to be 0. This is going to be 200, 1500, and 800. And now you notice I have 2 intersections now. I have an intersection here and an intersection here. So what I'm going to do is I'm going to add 100 to those points. And then, so I'm going to have 300, 0, 0, 200. Oop, that should be 100, sorry. Okay. All right. So now I draw the minimum number of lines, I'm just going through this, all right? So here's a minimum number of lines. Let's say I'll go down here, and then I can go across here to get 2 that way. And let me see, I can go across here, all right? So again, I have 3 minimum number of lines, and I have to go back to step 4 here. So what I'm going to do is I'm going to subtract 100 again from each one of my uncovered numbers. And so the first row is based, well, let's see here. Since the top Omaha is intersection, I'm going to add 100 to that. And then everything else is going to be what it was. And then coming down here to Smith's, it's going to be a 0. That's going to, next one's going to be 700. It's going to be 400. And then 0. And then coming down then to the Wilson row, it's going to be 0, 100, 1400, and then 700. And then finally coming down to the bottom row, I'm going to add 100 to each intersection. And then this is going to be 0. Okay? So if I look at the minimum number of rows here, I'm going to go that way, that way, that way, and that way. Okay? So now I have 4. Minimum number of lines to cover all zeros is 4, so I'm done. I can make the assignment. Now, to make the assignment, what I would suggest is to go to your last tableau here. And what you're going to do is you're going to look for a row or a column with just 1 0. Okay? So if I look at a row or column with 1 0, well, here there is 1 0 that represents Wilson, okay, and it's going to Omaha. All right, so what I can do, because you can see the Wilson row has only 1 0. So what I'm going to do here is I'm going to assign Wilson to Omaha, and it's going to cost me, if I go back to the original tableau, if I send Wilson to Omaha, it's going to cost me $500. Okay? So it's going to be 500. Okay, then once I make Wilson, I assign Wilson, then what I do is I cross out Wilson from being assigned anywhere else, and I cross out Omaha from being given anybody else, okay? So basically I cross these out. And then I go and look for either the row or column with 1 0. And again, I can see that it looks like it looks like Smith to New York has only 1 0. Here it is. Okay, so the Smith row has only 1 0. So I'm going to send Smith to New York, and that is going to cost me, if you look at the original costs, it's going to cost me $800. Okay, come back over here, $800. And then I eliminate Smith from being assigned anywhere else. So what I'm going to do here is I'm going to just cross out Smith from being assigned, and I'm going to cross out New York from being assigned anywhere else, okay? Okay, then it looks like we can send Jones to Miami. All right, so here it is. This row has only 1 0 now. So we're going to send Jones to Miami, and that is going to cost us $1,100. Okay. So Jones to Miami is going to cost us $1,100. And then we cross off Jones, and then again we're left with the dummy. So then the dummy, then nobody is going to go to Dallas. Basically, we'll assign the dummy to Dallas. So the total cost for this assignment is going to be the 500 plus the 1100 plus the 800, and so that's going to give us $2,400. And so that is the minimum cost combination of that you can get for assigning these 3 people to any one of 4 places. Okay, so I know that this example is a little involved, but the book does have this, but I wanted to just go through the example and highlight these steps because the book can be a little confusing. So any questions on this assignment example? Okay. All right, the second of the 4 topics in Chapter 15 is sequencing various jobs through one station. It's called single station scheduling. All right, so I want you to focus on only 3 rules. The first one is first come, first serve, which it means that we're going to sequence the jobs alphabetically through the station. The second sequencing rule is the shortest processing time, so we're going to sequence the shortest jobs first. And then early due date would mean we're going to sequence the earliest due jobs first. So we're going to evaluate these various sequencing rules looking at average flow time, average late time, and average number of jobs in the system. So I'm going to do a quick little example on how to use these various sequencing rules. So let's say in the problem we're given the following. We're given 6 jobs, A through F. Each job has its own processing time, and that's how long it takes to either assemble or complete it on the machine. And then the due date is shown in days from now. All right, so it'll take us, I guess these are in days, it'll take us 2 days to complete job A, and it's due 7 days from now. All right, so if we did the first come, first serve sequence, what we're going to do is just keep these jobs in alphabetical order. Now you will notice I've added 2 columns. The first is the flow column. And so this is just, what are the end times of each job if we do them in that sequence. So for instance, the job A, if we start at time 0 and complete it, it's going to take from time 0 to time 2. Then we would do job B, we would start at time 3, and it's again takes 8, so it's going to be done at job 10 or time 10. We're going to start C at time 11, it's going to be done 4 days later, or time 14, etc., etc. Now the longest time, or the time to get all jobs through the station, is called the make span time, and that's going to be 41 days. And then the 120 below that is just the sum of all the flow times. So the average flow is just the sum of the flow divided by the number of jobs. It's 20 days. And then the average number of jobs, it's kind of a congestion measure, is just the total flow divided by the make span, which is 3 jobs, okay? So any questions on how to calculate that flow column? So the late column is what you're doing is you're comparing the flow to the due date. So if the flow is less than the due date, then the job is not late. So for job A, you can see that the flow is 2, the due date is 7, so it is not late. For job B, it'll be done at time 10. It's not due till 16, so it is not late. Job C, on the other hand, it won't be done until 14. It was due at time 4, so it is 10 days late. And then job E will be done at 24. It was due at 17, so it'll be 17 days late. et cetera, et cetera. So that's how you calculate the late times. And so if you add up the total late, it's 54. So then the average late is 54 divided by 6 jobs, or 9 days late. So your goal here is to minimize these metrics. So is first come, first serve the best sequencing rule? Well, we don't know. It's we have to compare it to other sequencing rules to see if these are the lowest we can get. All right. So we'll try shortest processing time and early due date next, but are there any questions on this example so far? Okay, so this shortest processing time, again, you notice what I've done here is I've changed the order of the jobs, and I've started at the lowest time, and then the last job is the longest time, all right? So I've changed the sequence of these jobs. And again, the flow and the late are going to be calculated just like they were in the first example. I can calculate then my average flow, average late, average number of jobs. All right. And then with the early due date, again, what you can see is I have changed the sequence again. And what I've done is I've sequenced the earliest due date first. So job C is due in 4 days, job F, 18 days. So again, I've sequenced them with the shortest or the earliest one first. And again, I calculate my flow and late, just like I did with the other two examples, and then I can calculate my metrics. So if you compare the metrics now, you can see that the earliest due date is tied for the lowest average flow. It does have the lowest average late, and it's tied for the average number of jobs. So it is the best rule. It does the best job at minimizing those three metrics. So that would be how you can select the sequencing rule that's going to optimize your efficiency. All right, and that's basically all there is to single station sequencing. Any questions on this example? Okay, the third topic in Chapter 15 is two-station sequencing. And the best way that I can describe this is, so the rule is to find the minimum time at either station. If the minimum time is on the first station, you're going to sequence that job to the left. If the minimum time is on the second station, you're going to sequence that job on the right. All right, so if you look here, you can see that the minimum time here is this 2. All right, E has a time of 2, that's the lowest time. And so what we're going to do is we're going to sequence E to the left because it's on the first station. And so once we sequence it, then we're going to eliminate it from further consideration. And then we go and we find the next lowest. And so the next lowest looks like it's B. Now again, B is on the first station, so we're going to sequence it to the leftmost spot that we can, and then eliminate it from further consideration. And we just keep going along with this. All right, so then the next lowest one looks like it's F. Now, this one is on the second station. So what we're going to do is we're going to put it all the way to the right because it's on the second station. And then we'll eliminate it from further consideration. And then the next highest one looks like it's A. And again, it is on the second station, so we're going to put it to the rightmost available spot. And then we'll eliminate it from further consideration. And then it looks like, 6, which is C. It's also on So we're going to do the C in the rightmost spot, and then eliminate it. And then the next one's going to be, looks like D. It's on the second station. So we're going to put D next in the rightmost spot that's available, and then eliminate it. And then, you know, we just keep going on here. Then the next task is going to be, looks like it's going to be H. So we're going to put H here, and then the last task then by default is going to have to be G. All right? So this is our sequence of the sequence that is going to minimize the idle time at both stations. All right, so any questions on applying that algorithm to coming up with a sequence for two stations? Okay, so the next thing to do is to calculate the idle time. So the idle time, if we start here, let's say this is going to be 0, and then we're just going to increase time. Okay, so this is going to be time, and then this is going to be down here. This is going to be machine number, station number 1, and then station number 2 down here. So what we can do is we could do like a Gantt chart. Okay. So again, if we do E first, so let's just look here at our first station. Let's just look here at our first station times. So if we do E first, it's going to take us from time 0 to time 2. All right. So what I can do here is I can do an E. This is going to be E. And then this time up here is going to be at 2. And then the next one is B. Well, if I start B at time 2 and it's 3 units long, then I'm going to be done with B at time 5. All right? So then this next one here is going to be B. And then this is going to be time 5 here. Okay? Then I'm going to do G, and G takes 18 units of time. So it's going to take us out to time 23. And so we'll represent it like that. And so this is going to be G. And then we can start H at time 23, and it's 20 units long. So H is we're going to go out to time 43, which with H. All right, so this is going to be 43. And then this is going to be H. And then we can do D, and D takes 8, so that's going to take us to time 51. And then this is D. And then the next one's going to be C, so that's 9 long, so that's going to take us to time 60. I should have picked a shorter example here. Sorry about that, but hopefully, you know, this will make sense as we get along here. And then we're going to do A, so A can start at time 60, and it's going to take us to time 76. And then the last one is going to be F. F can start at 76, and it's going to take us to time 88. And then that's what the jobs on the first station are going to look like, okay? So any questions on kind of that Gantt chart of what things are going to look like on machine 1 with that given sequence? All right, so the next station, let's just look at the station 2 times, okay? So machine 2, we cannot start job E at time 0 because it won't be done until time 2. So we're going to start E at time 2, all right? And E takes 14 units of time on station 2, so we're going to be done with E at time 16. All right, so this is what this is going to look like. So it's going to start here at 2, and then it's going to be done at 16, okay? Now this time right here, this is what's called idle time, all right? Basically, machine 2 is sitting there waiting for E, and again, we'll assume there's nothing in it from a previous job. So it's just sitting there waiting, all right? And so what we're going to do is we're going to just do this Gantt chart on machine 2 in the same way, but we have to make sure that the item is done from the first machine before we can do it on the second machine. So B is next. Now B got done at time 5, so if we wanted to start B at time 16, that would be fine. It would be ready. So B takes 13, let's say, minutes on station 2. So we're going to go out to time 29 with B. All right, so there's no idle time there. So B, and this will take us to time 29. All right. Then G can start at time 29, and G takes 14. So this G is going to take us then to 43. All right, so G is going to be able to get started when H gets done on the first machine. Okay, so this is G, and this is time 43. Okay. All right, so we can start H at 43. It's done at time 43 on number 1, so we can start H at 43 on number 2. So H is going to take us 11 minutes, so that's going to take us to 54 minutes. So that's going to be about right here, not exactly to scale, but this will be H, and then this is, again, 54. And then we can do D, and D is done at machine 1 at 51, so we can start it at 54 on machine 2. So D takes us 7, so D is going to take us to time 61. All right, so then this is D, and then this is time 61. All right. Now we can C will be done at time 60, so we can do it at time 61 on machine 2. So C is going to take us 6, and so we will be done with C at time 67. All right. Now we have a problem here. We see that A won't be done until time 76. So what we have here is this machine is going to sit until time 76, and then we can start A. So this is going to be idle time here. All right. So this is looks like 9 minutes of idle time. So then A can start at time 76. It's going to take us to time 81. Okay, so this is A. And again, this is time 81. And again, we can't start F until time 88. And so again, this is going to be idle time here. And so we can start F at time 88. And then F is going to take us 4, so we'll be done with F at time 92. All right, so this is F down here, okay? So the total idle time with this particular sequence is going to be the 2 at the beginning, plus the 9, plus the 7. So it's going to be equal to 18, let's say 18 minutes, okay? Okay, so any questions on, so there's really 2 things with 2-station sequencing. It's number 1, using the algorithm to come up with the optimal sequence. And the second part of it is, putting that sequence on a Gantt chart and then tracking, the idle time that you get with the sequence. And the idle time will primarily be on machine 2. So any questions on this example? Okay, the last thing in chapter 15 is how do we schedule staff? All right. So let's say in this particular example, we need to we want to find the minimum number of staff we need such that each staff member gets 2 consecutive days off. All right, so basically, and we don't count Sunday in this particular example. Sometimes you do, sometimes you don't. So you can see Monday through Saturday is 6 days. So each person's going to work 4 days. That's full time. And we want to try to give them 2 consecutive days off. All right, so how this algorithm works is you're going to start with the first employee. So I'm going to just put employee number 1. All right, and then you're going to just transfer. These are staff needed, so you're going to just transfer the numbers from the first row to the second row. This is, again, how this algorithm works. All right, so what I've done here, well, hold on, let me undo that. Let me undo that. For some reason, that did not come out right. So here's number 1. And so all I'm doing is I'm just copying these staff needed numbers to the row below. Now what the algorithm says is it says identify the smallest of the 2 consecutive numbers. All right, so if I look at that, what are the smallest sum of the 2 consecutive numbers? I can see it's this 1 and this 2. All right. And so what the algorithm says is it says subtract 1 from all the uncircled numbers and bring the circled numbers down as is. So if I do that, I'll get something that looks like this. Okay, and so then this would be then available for employee number 2. Okay, so basically what I just did is employee number 1 is going to work Monday and Tuesday. They're going to have Wednesday and Thursday off, and then they're going to work Friday and Saturday. So again, they're working 4 days. And then they have 2 days off in a row. Now you keep repeating this algorithm until the possibility of getting a negative number occurs. Okay, so if I look at what is the smallest consecutive sum of the 2 numbers, well, I could do Monday and Tuesday. I could do Tuesday and Wednesday. I could do Saturday and Monday. All right, and there's a variety of ones I can pick. So what I'm going to do is I'm going to just go with Monday and Tuesday. Okay, so employee number 2 is going to have Monday and Tuesday off, and they're going to work Wednesday through Saturday. So again, what I want to do is I want to subtract 1 from all the non-circled numbers, and then bring the circled numbers down as is. All right, so if I do that, I get this. Okay, and so I keep going here. So employee number 3, I have to schedule that person. So I'm going to look for, again, this sum of the consecutive smallest 2 numbers. So it's going to be Wednesday and Thursday. That sum is 1, and that's the smallest you can get of any combination. So employee number 3 is going to work the same as employee number 1. They're going to work Monday and Tuesday and have Wednesday and Thursday off, work Friday and Saturday. And again, we're going to subtract 1 from all the non-circled numbers and bring the circled numbers down as is. All right, so now we're to the point here where if we continue with this algorithm, we're going to get a negative number. Okay, so let's say if we circle Monday and Tuesday, then when we go down to the next row, we're going to get negative numbers for Wednesday and Saturday, and that means we're overstaffed. All right, so now we're to the point where we can no longer ensure that an employee works 4 days and has 2 consecutive days off. In fact, anywhere that there's a 1 is going to be where that employee works. So employee number 4 is not going to be a full-time person. They're going to only work Tuesday, Thursday, and Friday. All right? And they're not going to get 2 consecutive days off. So the answer to this, the minimum number of staff you need are 3 full-time people and 1 part-time person. All right? The 3 full-time people are going to work 4 days a week. The 1 part-time person is going to work 3 days a week. Okay, so this is how this algorithm works. And again, this is in your book, but I wanted just to demonstrate it to you because the book is a little confusing in terms of, subtracting, from the rows and bringing down the circles and all of that. All right, so any questions on the staff scheduling algorithm? And that is basically chapter 15. Okay, you're saying, what? It doesn't sound like it's too basic. Okay, I just wanted to just spend the last 10 minutes talking about queuing. And again, we've been dealing with sequencing. And so queuing is it's a sequencing, well, it's not really a sequencing technique. It just looks at the impact of various lengths of the lines and how they arrive on the efficiency of the system. And so what we're going to look at is just a couple different characteristics of waiting lines. So we're going to look at let's say we're looking at a line of people at a amusement park. Well, how do they arrive? Okay, and so we're going to look at arrivals as a Poisson distribution, and a Poisson distribution is basically a skewed bell-shaped curve, all right? And then we're going to look at, once they get in line, do we limit the size of the line? Do we require first in, first out? So again, we are going to use limited lines, and the first one comes is first served, all right? And then the last thing about lines is how are people in the line served? So we're going to assume various channels, which is various line. The line splits up kind of like at the airport where you can go through, different metal detectors. And we're going to use a negative exponential or constant distribution to represent how service is delivered, okay? So a negative exponential is, again, service times are going to get lower as the probability of a longer service time gets shorter with the time as the service time goes on. Or a constant, it's just going to be 2 minutes each no matter what, okay? All right, so once we have these characteristics, what we're going to do is we're going to look at just a couple models. The first model that we're going to look at is MM1. So the M1 is a single channel. Okay, there's only one line, and people or units arrive first in, first out. It's a constant arrival rate. It's distributed as a Poisson. Service times, again, are negative exponential. And so the other assumption is the service rate is faster than the arrival rate, which means that the line will not continue to grow, all right? And so this is, in the book, there's like a whole bunch of equations for how to handle an MM1. But in problem number 2, the arrival rate is given as lambda, and that's 40 customers per hour. And then the service time is given, it's mu, and it is 90 customers per hour. So these are just rates. So these are how fast customers arrive and how fast they're served. And so if you wanted to calculate the percent utilization, it would just be lambda over mu. If you wanted to know the average length of the line, that's going to be something else sub q. And again, those formulas are given. And again, I don't want to go through each of these, but you can see once you've identified you have to identify 3 things. the type of problem it is, and then the lambda and the mu. And once you have that, you just pop in the numbers to answer the various types of questions about the performance of the system. Okay, and you guys can do that. I'm not going to belabor that point, but all these formulas are in your book, and you'll have access to them for the homework as well as for the exam. You just need to know how to apply them. Okay, so questions on this one? Okay, the next one I want to do an example of is with constant service time. So that's an MD1. So our assumption here is we have one line, and the arrivals are still coming as a Poisson, but the service times are constant. All right, so this one's a little different because the MM1 was service times were exponentially distributed, and an MD1 is service times are constant. So again, problem D16 is an example of this one. Again, you're given an arrival rate of 10 per hour and a service rate of 13.3 per hour. And the question asks, what is the average waiting time in the line? That's W sub Q. And what's the average length of the queue, which is L sub Q. All right. So again, by using these formulas and calculating these various, performance measures, you can, determine, if you need more servers. Like for instance, if the average length of the line or the average wait time is excessively long, you can again add more servers or figure out how to increase your service rate or do something so that people don't wait in line. Okay? As long as maybe they could, if the system was set up a little differently. So that is just for Module D, just understand those two types of models. There's a lot more models in there, but just those are the two most common ones. I think that should be enough for Module D. So any questions on anything that we've covered this evening? Any questions on the homework or the project or anything at all about the class? Okay, so as a friendly reminder, your Module D and Chapter 15 homework are due this weekend, and we're coming down to the end of the wire here. So if you do have any questions either on the project or on the homework, please feel free to post them to the discussion board or email me directly. The question is, will I post notes for Chapter 15 and Module D? I thought they were on there, but obviously they're not. So what I will do is after the call, I will post them. So they'll be available to you. My apologies, I thought they were on there already. Any other questions before we call it a night? Okay, everyone. Well, thank you for attending this evening, and good luck with the homework, and hope you are able to get through the homework effortlessly. Have a good evening now. Good night.